me just, before we get into tonight's stuff,
Okay.
and this is always kind of a problem, is that it's keeping current. They move so fast through AP Calc, whether it's AB or BC, they just move really fast through it. So
Right.
if we are not able to do one evening's work, we don't have time to get caught up on it usually. But I did want to mention this. The last part says use Euler's method to calculate f of 0.5. Well, that's a calculator problem. What kind of calculator do you have?
TI-84 plus CE.
Okay, well, you want to go in there and you want to find Euler's, hold on a second. There's some function that allows you to calculate Euler's method and gives you a table of values. Now, the one thing that you really need to know, and this is why I'm sure that D will not be on your AP test.
Okay.
But these kind of problems might be. Let's see. All right. Hold on. And I figured out how to solve this, actually. You got to download it, and then I got to open it with Paint, and it allows me to solve it. But this is from my Calc AB student.
Okay.
And she was given all of these to solve using Euler's method. And
Right.
if you tilt your head a little bit, you can see the first one is y prime equals x minus 1, and they give you an initial condition.
Okay.
I know how to do those now. The second one is y prime equals y minus 1, and they give you an initial condition. I know how to do that one. The third one is y prime equals a function of both y and x, y minus x. Don't know how to solve that differential equation, but I am looking at a differential equation with an initial condition, so I can use Euler's method on that also.
Right.
And Euler's method is a bit complicated. So if you want to cover it, we can. We can also look at that. You gave me a number of problems tonight that are going to be well in excess of a half an hour. So.
I did figure out Euler's method pretty.
Okay, cool.
I think for some reason Euler's method just makes sense to me, which is nice.
Well, it really does. If one were to describe it properly, it's basically the linearization.
Yeah.
In other words, you find a point that's on the curve that you're trying to solve for, and you take the derivative of that point, multiply it by the dx, and then you have the next y value. And then you do the same thing. And each iteration should be approximating that curve. So that's the whole point of Euler's method. But it really only has value if you can't solve the differential equation.
Right.
The simple ones, like the one they gave you yesterday, we were able to solve that differential equation. Who needs Euler's method? We know what it is. No need to approximate what f of 1.3 is. Just plug it in to what y is equal to. So, all right, let's look at this problem right here. Number 1, I assume you want to talk about?
Yeah.
Okay, I can load this into Paint, but since you took the picture vertically, I don't need to. Whenever you see this statement right there, that something, the rate of change in the amount of deer is directly proportional to the amount present.
Okay.
That applies to so many things in life. It's not just deer, it's people. If I know there's 5 billion people on the planet, I know that the rate of change of the number of people on the planet is going to be directly proportional to the amount present. Same thing with deer, same thing with bacteria, same thing with radioactive decay. If I start with 1,000 grams of some radioactive isotope, and I know that it's going to decay based on the amount that's present, then you have this situation. And the key formula, whenever you have something that is directly proportional, is this one right here. I'm trying to figure out where to write it. Let's write it right up here. And I could go through this proof, but I don't know that you really need that. Your calculus book does go through the proof. And the proof is an interesting proof, actually, as to how you get this, but you start with y prime is directly proportional. It's equal to k times the amount present. And you end up, based on that statement, if you solve that differential equation, you get this. And this equation covers all of these situations. Whenever something is directly proportional to the amount present, this is the equation that governs it.
Okay.
Now, the Wild Game Commission estimates there are 495 deer in the park. I tell you what, you're getting into an area where the degree of difficulty is getting harder.
Right.
Word problems in calculus are the hardest kind of problems.
Right.
So when you have problems like this, you got to get them to me a little bit further in advance.
Okay.
Mainly because I just had a session, so I didn't have enough time to cover these. And the harder they are, the more time I need. I really have no problem whatsoever in putting the time in.
Right.
But it's hard to do in real time. Let's see if we can figure out how to do this. I'm looking at a problem in the book that's very similar about population growth of fruit flies. It gives you the number of flies on the second day and the number of flies on the fourth day. And it says, how many did it start with?
Right.
Well, what do we know about this problem here? Estimates there are 495 deer in the state park. Which of those variables is going to be 495? In other words, that's at the beginning, right?
Right. I think, wouldn't it be the constant?
What is t equal to at that point in time?
T is equal to 0.
Correct. So if t is equal to 0, what is that equal to?
That's equal to the C.
Any number raised to the 0 power is equal to what?
1, or it's itself.
So that's 1.
Right.
Which means C must be 495.
Okay.
So I'm just going to start filling in some of these variables that I can figure out. And that's the first one. It is decided to reduce overcrowding. 10% of the deer will be removed from the park each year. What does that make K?
0.15 or 0.10?
Negative 0.1. In other words, K, this is a decaying exponential function. So we know that K, if it's growth, I'm going to write R, right? It's e to the RT. But if it's decay, it's e to the KT. But K is really the rate of decline, the rate of decay, which is going to be 10% a year. So now I can write this. I'm getting closer and closer to the actual function. In fact, that might be it. That's all we need. Notice that the only variable there is t and y. Y is going to be the amount of deer in the park after some period of time.
So it says solve the differential equation for P that models the situation. Would P be equal to Y?
Yes.
It would just represent what Y is.
Yeah, sorry,
I'm just making sure so like solving.
But yes. In other words, if P of t represents the number of deer in the park at the time t years, that's it right there. There's the equation for P of t.
Okay.
So I can say P of t equals 495 e to the minus decay rate, 10%, times time. What's the unit on time? Is it days? Is it months? Is it years?
Years.
It's in years. In other words, whatever the units are on K, same units on T. Now, it isn't always years. When you're dealing with bacterial growth, it's usually in days.
Right.
Which is fine. You can have T in any units you want. It's just that it's got to match the units of K. And they've told us that K is 10% per year. So if K is minus 0.1, then T has to be in years.
Right.
All right. So solve the differential equation that models this. I have a feeling I've jumped ahead by jumping to this. In other words, this is the differential. I've solved the differential equation that models it.
Yeah.
Okay. And let me kind of start from the beginning, which would be a better place to start. dy dt is equal to k times y. That is the statement that amounts to the first sentence. the rate of change, that's dy dt, of the amount of deer is directly proportional, so it's not k divided by y, it's k times y, to the amount present being y. So that's the differential equation they want us to solve.
Right.
Well, let's go ahead and solve that. Let me show you how to solve that. That's one of a crucial part of calculus, actually. dy dt equals ky.
Also, for the rest of the problems on this page, I can do the rest of the problems. A is the one that I have trouble with, so it's good that we're working on the first one.
Okay.
Because I just have trouble setting it up and knowing where to put.
I get it. From the first sentence, I can write this equation.
Okay.
Just like anything else. If I told you that a person's height is directly proportional to their weight, then you'd say height equals k times weight. Okay? So what this says is the rate of change in the deer population, which is that, is equal to some constant, k, there's always a k involved when you're talking about proportionality, times the amount present. So the rate of change is directly proportional to the amount present at any particular time. All right, how do we solve this? Well, first thing we do is separate the variables. I've got a dt over here. I'm going to put everything on the right side, and I'm going to put all the y's on the left side. Follow me here. With me?
Yeah.
Now integrate both sides. What do you get on the left?
LNY.
I had an appointment the other day with a pre-calc student. And she says, IN. Inverse. What's the inverse of AB divided by CD? And I was mystified. I could not figure it out. And we went for 10 minutes trying to figure it out. After I get off the phone with her, I realized she meant LN, not IN. But so now I kind of make it a point to write it as LN of Y.
Right.
The right side.
Well, how do you integrate k in terms of t?
Well, k is a constant. It's a number.
Okay.
So I can take it out of there and call it C.
So that makes sense.
CT. In other words, the integral of dt is t. So all I did is I removed the k outside the integral, and I'm going to call it c instead of k.
Okay.
We'll leave it called k, since that the standard format is in terms of k, actually. So we'll leave it like that. Okay, now I went over this with you last night, but the next step is not trivial. Do you remember what to do? This is a good step to remember. You're trying to solve for y.
Right. So I don't know what to call it. E both sides.
Hold on a second. I didn't do this correctly. There is still a plus c there.
Right.
I am taking an indefinite integral. And so I'm going to combine both plus c's on the right side and include that plus c. Yeah, the step is to exponentiate both sides to e. What's the left side become?
Y.
Okay, that's what we're trying to solve for. The right side becomes what? This isn't...
E to the kt plus c.
Well, how can I simplify that?
Well, it could be e to the kt times e to the c.
There you go. That's the trick. And it really is a trick. And it's a significant trick because it changes everything. Now, e to the c is just another c. E is a number. So if I take a number to that c, I get another c. This time I'm going to put it in front. So I get c times e to the kt. And that's how you get the equation based on what they gave us originally, that the rate of change is directly proportional to the amount present. Once you solve that, that's a differential equation. They ask us to solve it. This is what we get.
Okay.
So what is that? C e to the kt. Y equals. Okay, now let's go back and look at the problem. I figured out how to put your other document vertical. Okay, so our equation is going to be y equals c e to the kt, which is kind of where I started tonight's session at.
Right.
But I didn't realize that question A says solve the differential equation for that. And I can also call y p of x.
Right.
It's a function of x. Actually, it's not p of x, it's p of t. You have to put the correct variable in there. And the variable on the right side of the equation is t, not x.
Right.
Solve the differential equation that models this situation. We've done that. And now solve for k. Well, we know that and I did most of this already, but we know that at time 0, there's 495. So if I solve that, I get c equals 495. You with me?
Yeah.
Okay. So now we know a little bit more about that equation, which is p of t equals 495 e to the kt. Let's see. When solving for k, let's see, we got a 10% per year reduction. So this becomes 495 e to the minus 0.1 t. And there's our equation for the number of deer that are going to be present at any point in time. Did they ask? I mean, they're asking us to round our answer to 4 decimal places, but I don't see anywhere where they're asking about after how many years. Am I missing it? It says round it to 4 decimal places, but before we can come up with the number of deer, oh, they're asking us to round off k to the number of decimal places.
Yeah, which is, I'm confused at that.
I'm confused because it seems to me that k is definitely negative 0.1. So they've solved for k when they give us this information. And in my book, a very similar problem, you solve for, solve for c, which I did. And the problem in my book does not have a rate of decline, which they have given us. This is an unusual problem. In other words, it'd be an easier problem if they said, come up with this equation and then tell us how many deer are around at the end of 3 years. And then that's relatively easy. It's P of 3. Or how many deer are around at the end of 5 years? That's P of 5. They're asking us to solve for K, which leads me to believe there's something I don't understand about this. And I think I do understand it. I just don't understand why they're asking us that question A. Let me look at question B and see.
My teacher did post the solutions. I could look at it real quick.
Oh, please do. Well, yeah, go ahead. See what the solution. I think I know how to do B, but maybe we ought to look at the solution for A.
For A, it says K is equal to 0.1054. And he plugged in for P 495.5 equals 495 e to the kt, and that's how he solved for K, or e to the k1.
Hold on a second. Let's I hear what you're saying. So
I see what he did. He did after 1 year. He did 10% of 495.
So 495 equals C e to the minus k, and what did he put in for t?
T, he just did 1 year, and then he did 10% of 495, and that's what he set the equation equal to, like the equation that we found. So,
is there any chance he did it wrong? Or not? Did he ever make a mistake like that?
There is a chance, yes, but
Well, first of all, the problem does not state that there are 495 deer after 1 year.
Or no.
There are 495 deer at what I'm going to call base time, which is 0.
I think he wrote it wrong. He set the equation equal to 445.5 deer at year 1 because that's a 10% decrease.
Okay, so he's got this.
445.5.
445.5.
Yeah, and
that's based on a T of 1.
Yes. And then the C of 495.
Okay, that makes sense.
So that makes sense. Yeah, that makes sense how he did that. He just took what he know about the 10%.
Yeah. The only thing I don't get
it is a calculator problem.
Why K isn't minus 0.1. But if we solve this, so if I divide both sides by that coefficient, that's obviously going to be 0.9. So 0.9 equals e to the minus k. And I guess we can solve that by taking the natural log of both sides. And we get minus k equals the natural log of 0.9, which must be negative 0.1054. And
right.
That's how he gets k of 0.1054. So his solution then for part A is P of t equals C well, actually, that's 495 times e to the negative 0.1054 times t. So this is his answer to A, I presume.
Yes.
Okay. So he's got P of t equals 495, the initial amount, times e to that. I'm still a little not sure that's correct, but I'll go with it.
I'll ask him tomorrow why he did that as well, because
it seems
I
to
understand
me that this 10% dictates what k is.
Yeah, and which also brings up the question: why would they ask us to solve for k when they give us k? So, I will
exactly. Yeah.
I'll ask him that too, because it makes sense to me that it would just be negative 0.1 because that's the rate that the deer are being removed.
Especially in the exponent. In other words, if you'll remember growth, P equals e to the RT, right?
Right.
I always remember that because it's pert. Okay.
Yeah.
And R is, if you have 10% growth, then R is 0.1.
Right.
And if you have 10% decay, like radioactive decay, that's minus 0.1, then R is minus 0.1. Well,
Right.
this problem seems exactly perfect for 10% radioactive decay. You're losing 10% of the deer every year, which means the rate of change is directly proportional to the amount present, right?
Correct.
I'm going to lose 10% the first year because there's 495 present. The second year is only going to be 445 and a half present, and I'm going to lose 10% of them. Well, it seems like this whole function is structured so that k is that 10%, but I don't know for sure. I can't say that for sure, but that seems to me like what should be the case. Now, how he calculated k was also interesting, and I'm not quite sure why they come out different. They should kind of come out the same.
Right. I think the way you explained it was the way when I first reviewed this problem before I sent it to you. It's the way I thought that I would probably do it, even because I didn't really know.
Yeah.
But that's what my guess was what k would be. So,
right.
And logically, that is the rate that the deer is being removed.
Okay.
So,
well, I tell you what, since we don't know which one is correct, you'll find that out tomorrow. And maybe he can explain to you why k doesn't start right off at minus 10%.
Okay.
There might be a perfectly good explanation, and perhaps him setting after 1 year, realizing that there's 445.5 left, that allows him to solve for a k that's slightly different than negative 0.1054.
Right.
Nonetheless, we can do B. Unfortunately, B requires us to use that as our formula.
Right.
So B wants to know P of 5. Correct?
Correct.
So P of 5 is equal to 495 times e to the minus 0.1054 times 5. Now, this is another thing that I've always been a little bit puzzled by, and that is why they have this negative sign in front of k. When you have decay, the general formula usually has a negative sign in front of the k. You'll notice the k we came up with was a positive number.
Right.
So you need that negative sign. The thing is if you don't have the negative sign, if I said this was c times e to the minus kt, c times e to the kt, then k would come out to be negative and we'd be in the same condition. So I've been puzzled for 10 years since I've been tutoring this stuff as to why they put a negative sign in front of k. it seems like it's unnecessary to me. But nonetheless, this is a number you can get out of your calculator. In other words, there's no variable there.
Right.
I like the way it says rounded to the nearest deer.
Yeah.
And yet the way he came up with K was by saying there were going to be 445 and a half deer at the end of 1 year.
Yeah, I know.
So he rounded to the nearest deer to come up with K. I guess that's probably correct mathematically. K is, yeah, it shouldn't be based. For one thing, he's arbitrarily basing it on 1 year. Okay, what's number C say? Let's see. It's quite a bit past 8. We've done the hard part.
Yeah, I can do the rest.
The rest of it you can probably do.
Yeah, what helped today, especially, was going through the dy over dt.
That is big. Every calculus book out there, when they start the discussion on differential equations, they start it off by saying the rate of change is directly proportional to the amount there. So all discussions begin like that.
Right.
And solving that differential equation is what gives you this.
Right. You just explained it in a way that made a lot more sense to me than I've ever seen it. So thank you.
You're welcome. John, I will let you go, and I'll talk to you next time.
Okay. Thank you.